Hi, this is Shash Srinivasa. I'm a technical leader with the NSO engineering team. Today, we'll be speaking about the DCSN core function pack and how we use NSO to do cross-domain orchestration across data center and transport networks. So what are core function packs? Core function packs are NSO package bundles built by the NSO engineering team. We build core function pack to address specific use cases like transport SDN or NFVO. Core function packs are built to be customizable and they're built as reusable modular components. And it's important to note that core function packs are not complete solutions. Most of the core function packs do not come with custom UI, and we do not have assurance and statistics collection functions. So over the years, we've built multiple core function packs which address use cases in multiple networking domains. And the DCSN core function pack is our first cross-domain core function pack, which orchestrates both the transport or service provider networks and the data center networks. So you can build you can buy one or more of the core function packs and build your own end-to-end orchestration systems, combining any of them together. So let's look at why we need cross-domain orchestration across the data center and transport domains. So let us look at it from the data center perspective. If you look at your data centers have to cater to thousands of applications and millions of users. So as your data centers scale, the number of servers on your data center are increasing exponentially, and they can no longer fit into one rack or one floor or even one geographical location. So as your data centers scale across multiple geographies, your traffic between the servers, your east-west traffic, they have to pass through the transport network. And there is an urgent need to be able to monitor and control this inter-DC traffic that is passing through the transport network. So that's so for a massively scaled data center, the transport network is just an integral part of your data center network. So now let's look at it from the transport network perspective. So with the emergence of network function virtualization, what used to be hardware devices or appliances are now available as virtual machines. And you need to be able to spin up these virtual machines on servers. Servers are in data centers. So if you look at the traffic flowing in your in your transport network, it is making multiple hops along the data center networks and servers. So for a virtualized your telco DC, your DC is at the center of your transport network. So for these reasons, you need to look at both of these networks together and orchestrate them end to end. And that's what we aim to do with the DCSN core function pack. The solution is made up of two domains, the data center domain, transport, and the transport domain. In the data center domain, the networking hardware is the Nexus 9K series of switches, which has NXOS operating systems and APIC domain controller. On the transport domain, it's iOS XR series of routers, which is ASR 9K or NCS series of routers. The orchestration stack is made up of NSOs. You can have NSO in the layered service architecture. We need a minimum of 3 NSOs. The upper NSO is a cross-domain orchestrator, and you have at least one NSO, lower NSO for each domain, one for the data center domain and one for the transport domain. So since we are using LSA architecture, the lower NSOs can scale independently, depending on your data centers or transport devices. And if you need to scale the upper NSOs, you need to have multiple such sets of NSOs. The core function packs themselves, they're composed of smaller packages. Each of the NSO packages are versioned independently, and the function pack bundles all the required nets together. And it also has some utility packages like resource managers, which will let you do IP address allocations, as well as custom templates utils that will let you customize the core function packs. Our service models, the DC transport core function pack, it is designed for transport admins or cross-domain admins. It describes your data center and transport networks as one abstract model. So there are two sections in the model. The topology section, that's where you define your connections between your data center border leaves and the provider edge devices. And all your entities which are specific to your tenant is under the tenant container. On the DC core function pack, this is addressed to meet the needs of a data center admin. As you see, the models reflect closely with the managed objects in APIC controller. You have, though the names are the same, but we have done a lot of, we've studied the best practice guides and many customer configs, and we have minimized the number of required parameters. So if you look at our models, they're more intuitive and easy to use. So let's look at an end-to-end workflow. So we'll start with the user creating a DCT L3 VPN service. So this is a layer 3 virtual private network that will be created across multiple border leaves and multiple provider edge devices on multiple data centers, right? So in order to do this, you need to provide resources. Resources can be IP addresses, it can be VLAN numbers, it can be BGP AS numbers. So the user has two options. So he can either define all of these statically, or he can request the core function pack to fetch these resources from our resource manager. The default implementation of the resource manager allocates these values from a pre-configured pool. It can be an IP address pool or a VLAN pool, but you can customize the resource manager to fetch these values from external systems. So the DC3 L3 VPN service is using the reactive fast map model and is built as a nano service. When we make a request to the resource manager, a data kicker is created, waiting for monitoring the response path. And as soon as the resource manager responds, the service gets redeployed to proceed to the next steps. So we also have a deploy attribute that you can set on the service. It can be set to true or false. When a deploy is set to false, the service stops here, right? And it provides an opportunity for an admin to look at all the resources allocated, review it, and approve it. So you can also use our northbound notifications to trigger an approval workflow in ServiceNow or other such tools. So once the network admin is satisfied, you can set the deploy flag to true. At that point, the service is redeployed, and the DC transport CFP converts the L3 VPN request to multiple L3 out service creation request on the data center core function pack and DCPE connection service request on the DC transport core function pack. So these are the CFS, the customer facing services in the upper NSO. So they will consult the dispatch map, they'll figure out the affected devices, and the dispatch map will tell them the lower NSO instances that is managing these devices. The service requests are dispatched to the lower NSOs. This is where the fast map logic is applied on the RFS service in the lower NSO. The RFS service, it computes the minimum diffs in configs that needs to be applied to the affected devices, and they push that configs, the minimum diff set is pushed to their nets or network element drivers. So the nets convert them into the southbound protocols. Like the APIC net will make us multiple REST post calls. The iOS XR net will convert them into iOS XR CLIs. The entire operations are in a network-wide transaction. So if there are any errors, everything is rolled back. So we don't leave incomplete configurations on the network. So this is one of the features of the NSO platform. So once everything is successful, notifications are sent to the RFS and the CFS, and the CFS will mark the service as ready. So we've now created a layer 3 VPN between the border leaves and the provider edge devices. So we can do additional configurations on the data center side to filter and apply route policies. And also we can use the transport SDN core function packs to do SR policies on the transport network. And this will enable an end-to-end traffic flow across your sites. Now that you've seen all of these happen on slides, I will let Shujai show you a short demo. You can see this happening on a live network.
Thanks, Shash, for the presentation. So hello, everyone. This is Sujay here from the NSO application team. I will showcase a demo about the SR MPLS handoff that Shash has covered in his presentation. So as we all know that the DC transport use cases have support for both IP handoff and SR MPLS handoff, but I'll showcase the demo on SR MPLS handoff on a real network. So as part of this demonstration, I have a 3-node NSO setup in one node as CFS and 2 nodes as RFS, running the data center core function pack and the data center transport, and a single leaf connection connected to the VM and a border leaf connected to the DCP network. As part of the demonstration, we want to showcase the use cases for port configs, tenant services, DC interconnect, and finally testing the connectivity between the DCP and the VM behind the leaf switch. So as part of this demonstration, I have a pre-configured the tenant service and the port configuration service. I'll walk you through the DC interconnect to set up the SR MPLS BGP, EVPN, and LU session, and finally associating the tenant configuration to allow the VRF on this session. And to enable the traffic, we will associate the contracts needed for this traffic enablement. So as part of the configuration, what we have for DC transport SR handoff, we are using the resource pools that was pre-created. We will associate the resource pools to the topology, have the topology settings for the ACI border leaf and the PE connection to set up the BGP, EVPN, and the LU session. What are the resource pools that have been allocated? That is on the border leaf and the DCPE side, we have the EVPN loopback, the transport loopback, and the IPv4 addresses for the EVPN session between the DCP and the border leaf. So let me quickly switch pane here to show you on the NSO UI. So what we have on this session is I have already pre-created the interconnect session as a deploy set to false for the EVPN. So what we will do is set this to true to enable the EVPN and the LU session. Look at the commit manager for the dry run of the configuration that is pushed to the data center RFS nodes for the core function pack, DC core function pack, and the data center transport core function pack RFS node. So what we see on the configuration is on the DC controller, it is creating a route policy service, an L3 out routing service for the DC interconnect. And on the DCP connection, it is adding an endpoint DCP1 to create the EVPN BGP session. The respective configuration on the device RFS nodes for RFS1 and for RFS2, and the respective configuration that is pushed through the epic. So this shows the vast scale of how the automation orchestration is useful to create a EVPN and LU session on the devices between border leaf and the DCPE node. So let me go ahead and do a commit. And so once this configuration is applied, we can see what are the configurations that is pushed to the border leaf nodes on the EPIC and on the DCPE side. So on the DCPE's device, we will see the EVPN loopbacks that is created for the border leaf and the respective neighbor commands configured on the router BGP session for the BGP EVPN and the LU config. The right side shows the BGP neighbor output and the show BGP sessions. So once this is established, we will have the tenant created to allow this tenant service, tenant SCVT 11, to be forwarded using the SR-MPLS link under the infrastructure or the topology that was created. And I've attached the export route policy as outbound route map to the service. So on the configuration, let's go to the DCP network. On the tenant service, we have the L3 VPN created and the deploy set to false. So let me enable this to true, and let's go to the commit manager to see what is the dry run of the config that is being generated for the DC L3 VPN service to be passed through the SR infra L3 out. So on the local node, it is creating on the CFS the DC controller service. EPIC NSO is adding the new L3 out routing service. On the device RFS, you will have the L3 out routing service created. On the RFS for the DC transport, you will see the DCPE connection for the DCPE switch. And the configuration on EPIC, what is the route targets that will be stitched on the DCP side, which will be import export on the SCVT VRF for the tenant SCVT 11. And on the BGP side, the stitching configuration for the route targets for import and export is configured. So let's go ahead to do a commit. So at this stage, the tenant SCVT 11 configuration is allowed on the SR-MPLS infra L3 out service. So what is the configuration that is applied to the devices is, one is the resource pool allocation, which is created automatically using the resource pools. The validation of tenant. So here if you see the SR-MPLS VRF L3 out is created adding the SCVT VRF 11 and the outbound route map. And finally, the route target stitching, which is created on the DCPE switch. But as you can see that the ping is still not successful. This is expected because we are still missing the tenant L3 out EPG to be associated with the L3 out and a contract association. So the final step is to configure the DCT L3 out. That is the configuration to associate the L3 out security service between the SR-MPLS DC interconnect session and associating the contract. And once that is associated, we will see that the infra L3 out is pointing to the service, new tenant EPG is created, and this association will ensure that we have the valid connectivity between the EPG1 to the BD IP address. So that is, if you see here, the ping association should be successful. So let me show you here quickly for this. Let me create on the config is load the configuration for the L3 out security service. So let me paste this here on the device, load, and the configuration is associated here. Let me do a push on the service. So as this is pushed and created, let me log into the device to see what is the configuration and pushed on the service. Since this is enabled, I can now do a ping between VRF SCVT VRF 11, 11.11.11.11 on source loopback 102. So this will ensure that the connectivity is established between the DCP and the VM. So this is a short demo. So going back to the slide deck, I mean, we have validated the connectivity between DCP to the VM. We have established the connectivity on the EPG1 and the bridge domain that was used for the tenant service. So the final key takeaways, using the NSO core function pack, we have demonstrated the end-to-end traffic on a live network using the core function packs, and it is really helpful and seamless for the deployments. Thank you for watching. Have a good day.